Welcome to the bonus multiple choice review video for Chapter 7. I've got 11 multiple choice questions that we are going to go through together. So number 1, researchers conducting a study of voting chose 663 registered voters at random shortly after an election. Of these people, 72% said they had voted in the election. Election records show that only 56% of registered voters voted in the election. Which of the following statements is true? So if you look at our multiple choice answer options, we're just trying to identify that if is the 72% and the 56% in the problem, are they parameters versus statistics? Or I guess we should look at answer choice A here. It's saying 72% is a sample and 56% is a population. And what I would say is 72% is coming from a sample, but it is not the sample itself. And 56% is not the population, but it is coming from the population. So I can tell you up front that A is definitely going to be off. Now, parameter versus statistic, which is which? A parameter is any value that comes from the population, and a statistic is any value that comes from a sample. So we just need to differentiate. The 72%, where is it coming from? So of these people, 72% said. Well, of these people, where are those people coming from? Well, they're coming from a study of voting that chose 663 registered voters at random. To me, that feels like the 663 people that were chosen at random are a part of a sample. So I'm getting the vibe that the 72% is a statistic. So B says 72 and 56% are both statistics, so this one's still valid so far. 72% is a statistic, true. 72% is a parameter, incorrect. That is not coming from the population. And 72% and 56% are both parameters, not true. So now we need just to determine the 56%. Now it says election records show that only 56% of registered voters voted in the election. Now, this one can be a little tricky here, but who votes on election day? And that would be all of the people have the ability to vote on election day. So this 56% number is really referencing the population proportion that voted in the election on election day. So it is a parameter value. So it is not a statistic. So it is not answer choice B, and it truly is only answer choice C. Number 2, a polling organization decides to increase the random sample size from 1,500 to 4,000 voters before an election. Its latest poll is designed to estimate the proportion of voters who favor a new law banning smoking within 100 feet of public buildings. What is the goal of this increase in the sample size? Now, answer choices A and B focus on about the bias of the estimate. Answer choices C and D talk about an increase or decrease in the variability of the estimate. And E focuses on both, that it helps to reduce the bias and the variability of the estimate. Now, if we increase our sample size, if N increases, then the one thing I can definitely remember about this chapter is when we talked about when the sample size increased, what happened to our spread or our variability. And the variability, the spread, I'll just call it spread because we either had sigma, sub, a lot of different subscripts, but the spread went down. So we actually will reduce the variability of our estimate. So it's definitely not C, but we also need to discuss, is it possibly going to reduce the bias? Because we do want to reduce the variability, but is it also going to reduce the bias? Or is the answer truly just D? So I know it's reducing the variability, so it's not purely just A and B, but it's definitely D or E. Now, the reduction in bias of the estimate, it really doesn't matter what our sample size is because our estimate should be hopefully very close to the actual true parameter value. And so an increase in the sample size really isn't going to reduce or increase the bias because of the features of a sampling distribution. The center should be relatively close to the actual value. So I would say it doesn't actually reduce the bias, but its key feature is that it reduces the variability of the estimate. Number 3, suppose we select an SRS of size n equals 100 from a large population having a proportion p of successes. Let p hat be the proportion of successes in the sample. For which value of p would it be safe to use a normal distribution to approximate the sampling distribution of p hat? Now, they're talking about what value would it be safe to have a normal distribution. So this is making me think of the shape condition, where n times p had to be greater than or equal to 10, and n times 1 minus p would also have to be greater than or equal to 10. And they give me a sample size to work with up here that n equals 100. So let's solve for p in both of these situations, and let's see what values of p would work. So in this scenario, we would just divide the 100 over to get p has to be greater than or equal to 10 divided by 100 would be 10%. So p has to be bigger than 10%. So, or at least 10%, I should say. So I know the answer is not A or B. So that leaves me with C, D, and E. And if I were to solve the other inequality, then 1 minus p has to be greater than or equal to 10%, which would mean that p would need to be smaller than 90%, or at most 90%, I should say. So p has to be bigger than 10%, at least 10%, but at most 90%, so it can't exceed 90%. So that's going to eliminate D and E, which leaves me with answer choice C. So 0.85 would be a value of p where the normal condition would be satisfied. Number 4, the central limit theorem, the CLT, is important in statistics because it allows us to use a normal distribution to find probabilities involving the sample mean in which of the following settings. So when the sample size n is large for any population, when the population is normal for any sample size, when the population is normal and the sample size is large, when the population is normal and the population standard deviation is known for any sample size, and when the population is large, regardless of shape. Now, the central limit theorem was about having a big enough sample size, and really it applies to any type of population, whether that population was normal or not normal or unknown. It didn't matter what the size or what the shape of the population was, as long as we had a large enough sample size. That was the only thing that really mattered. So I would say the correct answer would be A. Number 5, a lot here. The number of undergraduates at Johns Hopkins University is approximately 2,000, while the number of students at Ohio State University is approximately 60,000. At both schools, an SRS of about 3% of the undergraduates is taken. Each sample is used to estimate the proportion P of all students at that university who own an iPod. Suppose that, in fact, P equals 0.80 at both schools. Which of the following is the best conclusion? Now, they're going to talk about and this is where I kind of want to focus my attention initially, because the population is smaller, because it is based on a smaller sample size, because the population is larger, because it is based on a larger sample size, because both samples are 3% of their populations. So they're focusing on one of two things, really, it seems like here. They're either focusing on the fact that one school's population is smaller than the other, and that one school's population is larger than the other, or is it based on the sample size? So, and then we're also talking about the estimate. The estimate is closer to the truth for one school versus the other. Oh, let me go back to there. There we go. And so one thing I would consider here is we do need to consider the sample size. And even though it's 3% at each school, it's 3% of different values in the end. So at Johns Hopkins, 3% of 2,000 students would be, 60? So at Johns Hopkins, where am I going to write this at? I've practically got no room. Let me scoot this up here. We'll go right there. So the sample size at Johns Hopkins is really 60. And then the sample size at OSU, at Ohio State University, 3% of 60,000 would be what? 180? So Ohio State does have a larger sample size, which means in the end that its variability would be smaller. And if the variability is smaller, that means it's squeezing in all of our estimates. And so I would say that the Ohio State one, the estimate from Ohio State would be closer to the truth just because it has less variability. It's squeezing in all of those p-hat values that we would get from samples. It's squeezing them in closer and closer and closer to the actual true value for the entire population, which is supposedly 80% here. So I would expect the estimate from OSU to be closer, not because the population is larger, which it is true the population is larger, but that's not the reason why the estimate would be closer to the truth. But it is because it is based on a larger sample. So I would say the correct answer would be D for number 5. Number 6, a researcher initially plans to take an SRS of 160 from a certain population and calculate the sample mean X bar. Later, the researcher decides to increase the sample size so that the standard deviation of the sampling distribution of X bar will be half the size. What sample size should be used? Now, a lot of people would initially think that if we want to cut the standard deviation in half, well, then we would just, here, before I get ahead of myself here, we know that for the standard deviation to be smaller, we need to take a larger sample size. And so now, this is what I was trying to say, that if it's going to be half the size, then people would kind of naturally think, oh, well, we just need to double the random sample because that'll have the same kind of effect, but in the opposite direction. And that's good logic, except there's one issue. That the standard deviation formula, and in this case for a sample mean, is sigma divided by the square root of n. So mathematically, if I wanted half of that standard deviation, I would algebraically really need to multiply the other side of this equation by 1/2. And then if I wanted to multiply my fractions together here, this would really be sigma divided by 2 times the square root of n. Well, now if I wanted to get that 2 underneath the square root with the sample size, I'm going to actually need to square that 2. So it's really sigma divided by the square root of 4n. And then there is the key. I really want to take 4 times the sample size. So 160 originally, and I want to quadruple it to actually cut my standard deviation in half. So I would really need a sample size of 640 to be able to accomplish that. Number 7. The student newspaper at a large university asks a simple random sample of 250 undergraduates. Do you favor eliminating the carnival from the end of the year celebration? Why would you want to eliminate a carnival? Why would you do that? I don't know. In the end, 150 of the 250 sampled are in favor. Savages? What? You want to get rid of a carnival? Are you anti-fun? Where do you go to school? Suppose that unknown to you, 55% of all undergraduates favor eliminating fun. Wow. Way to go, guys. If you took a very large sample of simple random samples of size 250 each from this population, the sampling distribution of the sample proportion p hat would be. So let's take a look at shape. So we've got all this split down into shape, center, and spread. Here we go. And let's see, what would be the easiest thing? Ooh, I remember that mu sub p hat. And this formula will be given to you on the chapter test because it's given to you on the AP exam. But mu sub p hat, the center, is really just the population proportion p. And so in the end, it says, suppose that unknown to you, 55% of all undergraduates. So the 55% is the population proportion. So it's not 60%. It is 55. So that's eliminating C and D. And now if I go back and take a look at, take a look at the standard deviations on all these. It must be 3%. So do I actually need to go calculate what sigma sub p hat is with that formula? No, I really don't, because it's going to be 3% according to all 5 options here. So I don't get any help from the standard deviation. So now I got to determine, is it exactly normal, approximately normal, or skewed right? And so nothing in life will be exactly normal. But we are shooting for approximately normal. But we had a condition to check for that. So let's move, no, hold up. Let's move this up here. So we were looking at, SRSs of size 250. Okay. So N equals 250, and P is our 55%. So we had to check N times P, is that greater than or equal to 10? And is N times 1 minus P greater than or equal to 10? So 250 times 55%, am I going to get at least 10? Yeah. And if I had 250 times 45%, am I going to get at least 10? Yeah, both of those are easily going to be met. So it will be approximately normal as the shape of the sampling distribution. So I would say the correct answer would be B. Number 8. Which of the following statements about the sampling distribution of, the sample mean is incorrect? The standard deviation will decrease as the sample size increases. The spread's going to go down as the sample size goes up. Yeah, no, that's a true thing. But again, remember, we're looking for the incorrect statement. So it's not A. The standard deviation measures how far the sample mean typically varies from the population mean. And that's really the definition of a standard deviation. It gives us that average difference between each value and the mean. But in this scenario, the sampling distribution, each value is a sample mean. And what is the mean of the sampling distribution? Well, it is the population mean overall. So this is also a true statement. C, the sample mean is an unbiased estimator of the population mean. And that's a true statement. That's why we do mean problems and proportion problems, because the sample mean is an unbiased estimator of the population mean, and the sample proportion is an unbiased estimator of the population proportion. So that is a true statement. Cross it off. D, the sampling distribution shows how the sample mean is distributed around the population mean. So how the sample mean is distributed around the population mean, this kind of goes hand in hand just about with the standard deviation definition up here in B, that we really have all of these X bars, all these sample means in a sampling distribution, and they're all kind of hovering right around, they're centering all around the true population mean. So that is a true statement. So E must be the incorrect one. And let's take a look at it. The sampling distribution shows how the sample is distributed around the sample mean. So number one, it's not around the sample mean. We want it to be around the population value. And it's not just how the sample is distributed around the sample mean. I mean, we get the sample mean from the sample itself. Number 9, a newborn baby has extremely low birth weight if it weighs less than 1,000 grams. A study of the health of such children in later years examined a random sample of 219 children. Their mean weight at birth was 810 grams. This sample mean is an unbiased estimator of the mean weight mu in the population of all such babies, which means, okay, so we need to kind of figure out what does it mean to be an unbiased estimator. So the definition of an unbiased estimator, again, because I think we mentioned it earlier, was that the center of the sampling distribution is roughly the same as the true population parameter. So we need the center of the sampling distribution. We need it to reference the population proportion. So in all possible samples of size 219 from the population, the mean of the values of X bar, so this initial part here is basically saying create a sampling distribution in all possible samples of size 219, the mean of the values of X bar. We're creating this sampling distribution of all these X bar values, but it's going to equal 810. But we don't want it to equal 810. 810 was the mean weight of a sample. So the 810 really isn't that special of a number overall, because it's not the population value that we're trying to equal or trying to be roughly the same as. So A is out of the question. Now in B, in all possible samples of size 219 from the population, the mean of the values of X bar, so again, this is saying create the sampling distribution. So the mean of the values of X bar, the mean of the sample means, okay, this is basically saying the center of the sampling distribution will equal mu. So yes, mu sub X bar equals the population mean mu. So B is what it really means to be that unbiased estimator. That's why this formula worked for the center, was because X bar is an unbiased estimator of the population mean. Number 10, an SRS of size 100 is taken from population A with P equals 0.80. An independent SRS of size 400 is taken from population B with P equals 0.50. The sampling distribution of the difference A minus B in sample proportions has what mean and standard deviation? So they want to know what is mu sub P hat sub A minus P hat sub B, and what is sigma sub P hat sub A minus P hat sub B. What do those come out to be? Now, the mean is going to be the easy part, but if you look at the mean choices, the answer is going to be 30%, right? Because we are going to just subtract the two population proportions, and on average, there is a 30% difference between those two populations. So we don't really get any help by looking at the mean. It's the standard deviations where it's really going to make the difference. So this ended up being giant square root. And then this would be P sub A times 1 minus P sub A divided by N sub A. And then we do the same thing with population B. P sub B minus 1 minus P sub B divided by the sample size of B. So big square root, really we've got what? 0.80 times 20% divided by, and they said sample size of that one was 100, plus, and then it's really 50-50 divided by not 100, but they increased the sample size to 400 for that one. So we got to figure out, what does that come out to be exactly? So if I were to take my calculator and go square root 0.8 times 0.2 divided by 100 plus 0.5 times 0.5 divided by 400, I get about 4.7%, which looks like answer choice C. And the final question. Now this one actually came from an old AP Stats exam multiple choice test. And it says the graphs of the sampling distributions 1 and 2 of the sample mean of the same random variable for samples of two different sizes are shown above. Which of the following statements must be true about the sample sizes? So the sample size of 1 is smaller than 2, 1's bigger than 2, 1 sample size is the same as 2, the sample size doesn't affect the sampling distribution, or the sample sizes cannot be compared based on these graphs. Now, what I notice is both of these sampling distributions are centered right around 10, but I notice that the spread is different, that there is more variability. There's more spread with distribution 2, and there is less spread in distribution 1. And so if there is less spread, then that must mean the sample size must be larger, right? Because we said as the sample size increased, our variability or spread decreased. So distribution 2 must have a smaller sample size, and distribution 1 must have a larger sample size. So I would say the correct answer for the last question is B. Good luck studying for your test. I know you'll do great.